Alright, this is the last video, video number 4 of this particular lesson. And in this video we're going to take a look at the difference between nuclear reactions and chemical reactions. And to do that, we're just going to start right here, right in your notes, and try to outline that a little bit. So let's take a look at, actually we're going to start with chemical reactions. I changed my mind. Alright, chemical reactions. This is basically removing an electron from hydrogen, or another way to think of a chemical reaction is an exchange of electrons. So if electrons go from one object or one atom to another atom, that's what we classify as a chemical reaction. Now let's take a look at this. How does that work? Well, we know that we have the nucleus right in the center, okay, and surrounding that are going to be basically electrons. And so here's an electron here. Here's another shell. Here's another shell. What do we say? I think there's 2 on the first shell. There's 8 on the second shell. And I think upwards of 8 on the second shell, right? Let's see, 1, 2, 3, 4, 5, 6, 7. There's 8. Okay, so now think about this. I'll do the hydrogen in just a moment. I'm just going to do a generic atom. To remove one electron just means requires me to come in, grab this electron, and pull it off. Well, what's going to prevent me from doing that? Keep in mind that the nucleus is positive right there. It's a big positive charge sitting right in the middle. And so if I remove this electron, which is negative, that electron doesn't want to leave because it's attracted to this positive. So for me to remove this electron means I have to overcome what's called overcome what's called the electromagnetic force. Now you might think, ooh, the electromagnetic force, that's a big force. Well, it is. If you had to rank all 4 forces in nature, there are 4 of them, the electromagnetic force would rank the second most, or second strongest, you could say. So it is tough, but it can be done. Alright, now let's be specific. Let's go to hydrogen. Hydrogen, we know, has 1 proton in the nucleus and 1 electron. This is ordinary, normal hydrogen. So if I'm going to remove this electron, I have to remove the electron and remove it from this proton, essentially. And scientists have measured that energy. And the amount of energy needed for that to happen is 13.6 electron volts. Now, keep that number in mind because it's going to be very important. Okay, now I'm going to go over here and take a look at nuclear reactions. Well, in a nuclear reaction, I have the nucleus. The nucleus is going to have some protons and some neutrons. So we'll put some in there like that. Let me zoom this in. And then around this, obviously, we're going to have some electrons. And I'm not too concerned about the electrons right now. To have a nuclear reaction, what has to happen is I have to essentially take either a proton or neutron away from the nucleus. And for that to happen, I have to reach in and grab a neutron. If I do that, that means I'm not trying to overcome the electrons or the electromagnetic force. I'm trying to overcome the force that binds protons and neutrons and protons together. And that force is called the strong force. And the strong force ranks number 1 among all forces in nature. As a matter of fact, if my numbers are right, I think it's around 37 times stronger than the electromagnetic force. So to remove a proton or an electron requires much from a nucleus, requires much more energy. And that's why the nuclear reactions have more energy associated with them, because you're not trying to overcome the electromagnetic force, you're trying to overcome the strong force. And that's a big difference. Okay, so let's be specific. If I were to remove, let's say I had an iron nucleus, so here's iron 56. There's the nucleus of iron 56, and let's say there's one nucleus, or one neutron in iron 56. If I were to remove that one nucleon from iron 56, how much energy does it require? Well, we've calculated that already. I think you did it in worksheet 1-2. To remove that one neutron requires, let me get this right, here it is, 8.81 mega electron volts. You might be saying, well, that's no big deal. Oh, remember, mega is like a million. So this is 8,810. Those two numbers are the same thing. It's 8.8 million electron volts. That's a lot of energy. Check out the amount of energy to remove an electron over here. Remember, that was 13.6 electron volts. So you're talking millions times stronger. And the fact that it's million times stronger leads us to the conclusion that there's much more energy associated with nuclear reactions than with chemical reactions. All right, let's flip this over and let's do the key concept box and wrap up our last video. So basically, this is just a review of what we talked about. Chemical reactions involve the exchange of electrons, while nuclear reactions involve the transformation of nucleons. If I can spell nucleons. There it is, there it is, there it is. I'm sure you're making fun of me and laughing at me right now. There it is, nucleons. To remove an electron, next one, to remove an electron. Now, to remove an electron, we call that binding energy. Oops, I'm ahead of myself. We call that a chemical reaction. You only have to overcome, so to chemical reaction, you only have to overcome the electromagnetic force. To remove a nucleon from a nucleus, now that's going to be a nuclear reaction because we're removing something from the nucleus. Excuse me, you must overcome the strong force. While it takes, let's see, how many electron volts of binding energy to remove an electron from a proton? Well, that's 13.6. It takes how many mega electron volts did we say? Let me flip it over and look. It was 8.81 mega electron volts. That's an incredible amount of energy. So therefore, nuclear reactions, removing nucleons, have much more energy than chemical reactions, and that's removing electrons. And there's the end of video 4. You got a few questions left, and the test is coming up. Good luck.